68 miles every second. That's how fast the Andromeda Galaxy barrels toward us right now. The universe keeps expanding and galaxies usually run from each other. But Andromeda charges straight at the Milky Way like it picked a fight. That motion never made sense until now. Most galaxies behave like dots painted on a balloon. Blow the balloon up and every dot moves away from the others. That's how cosmic expansion works. Space itself stretches, carrying galaxies with it. But Andromeda ignores that rule. It approaches us at roughly 150,000 miles per hour, and that puts it on a direct collision course with our galaxy. Scientists knew about the future crash for years, but they never fully understood why Andromeda overpowered the universe's expansion in the first place. Now, they figured out that both galaxies sit inside a massive, flat sheet of dark matter. You can't see it, but you can see what it pulls on as it has gravity. Instead of forming a neat ball around the galaxies, this dark matter spreads out more like a gigantic pancake, stretching across millions of light years. And that flat shape changes everything. Gravity works like tension in a stretched rubber band. Put a bowling ball on it and the fabric dips. Roll a marble nearby and it curves toward the heavy ball. The Milky Way and Andromeda sit on the same stretched sheet of dark matter. That sheet doesn't pull evenly from all directions like a sphere would. It pulls more strongly along its flat plane. That uneven tug slows the outward motion of nearby galaxies and pulls Andromeda inward. And space doesn't just contain galaxies, but also enormous empty regions called cosmic voids. These regions expand faster than average because they hold less matter. When they stretch outward, they push matter toward their edges and build dense walls of galaxies and dark matter around them. The Milky Way and Andromeda sit near one of these cosmic walls. The faster the void expands, the more it funnels matter into the surrounding structure, and that reshapes how gravity flows through our neighborhood. So instead of two lonely galaxies drifting toward each other by accident, it's a whole landscape that's shaping their motion. Dark matter forms the terrain. Voids carve out valleys and ridges. Gravity acts like water running downhill. Andromeda doesn't just decide to approach us. The entire structure of our local group, that's the small family of galaxies that includes us, guides its path. That local group stretches about 10 million light-years across. Each light year equals nearly 6 trillion miles. Even at 68 miles per second, Andromeda still needs about 4.5 billion years to reach us. That sounds comfortably distant, but in cosmic terms, that's basically tomorrow. Earth formed about 4.5 billion years ago. The timeline of our planet and the countdown to this galactic collision almost match. When the two galaxies finally meet, they won't smash like solid objects. Galaxies mostly consist of empty space, and stars sit trillions of miles apart. During the merger, most stars will slip past each other without direct impact, but gravity will twist everything. Long tidal tails, huge streams of stars, will stretch out like glowing ribbons. Gas clouds will collide, spark furious waves of star formation, and light up the darkness. Over billions of years, the Milky Way and Andromeda will blend into one giant elliptical galaxy. A rounder, puffier system that astronomers sometimes nickname Milkomeda. Alright, but what about us? The solar system will likely survive the chaos, but it won't stay untouched. Our position inside the galaxy could shift dramatically. We might move farther from the galactic center or swing into a new orbit entirely. The night sky will transform. Andromeda already appears as a faint smudge about 2.5 million light-years away. Over the next few billion years, it will grow larger and brighter until it dominates half the sky. Stars will scatter into new patterns. Constellations will lose their shapes. The sky your descendants see won't resemble the one above you tonight. So, for decades, scientists assumed Andromeda approached us simply because gravity between the two galaxies overpowered expansion at short distances. That explanation worked, but it left gaps, such as why that exact speed and why that specific trajectory. The new research shows the motion doesn't come from just two galaxies tugging on each other. It comes from a whole invisible architecture. dark matter sheets and expanding voids, shaping space like scaffolding behind a building. Dark matter itself still remains one of the biggest mysteries in physics. It doesn't emit light, and telescopes can't photograph it directly. Scientists detect it by watching how galaxies rotate. Stars at the edges of galaxies move faster than visible matter alone could allow. Something unseen adds extra gravity. That something makes up about 85% of all matter in the universe. Regular matter, that's everything you can touch, makes up only about 15%. You live in the minority material. In fact, new research shows that even the supermassive black hole at the heart of our Milky Way is a supermassive but compact clump of dark matter. That dark matter might be made of super light particles called fermions that can clump together into an extremely dense core surrounded by a wider, fuzzy halo. This structure could reproduce everything we've observed around Sagittarius A star, the Milky Way's supermassive black hole. Everything from the crazy fast orbits of stars right near the center to the slower rotation of stars further out in the Milky Way. So, this massive dark matter clump would put out the same gravitational pull that we've been attributing to a black hole all this time. One of the most famous pieces of evidence for a black hole in our galaxy came in 2022, when the Event Horizon Telescope captured an image that looked like a shadow. A dark circle surrounded by glowing gas, right where Sagittarius A star should be. But new models suggest this dark matter core could cast a shadow that looks almost identical to the one we saw in that image. It means our best visual proof of a black hole might not be what we think it is after all. The study leans on data from the European Space Agency's Gaia mission, which maps how stars move with astonishing precision. That data shows a kind of slowdown in orbital speeds far from the galaxy's center, called a Keplerian decline. The dark matter clump model can explain both this and the rapid motion near the center simultaneously, something older models struggled with. Before we jump to conclusions though, scientists emphasize that this isn't proof that the Milky Way's central object isn't a black hole. It's just that this dark matter explanation seems to fit the observations perfectly well, and might even do a better job explaining some features than the traditional idea. Upcoming observations, especially more detailed looks at the photon rings that light makes around black holes, could help tell the two ideas apart. The idea that dark matter forms a vast, flattened structure around the local group reshapes how we picture our cosmic neighborhood. Instead of a simple, roughly spherical halo, there's something more like an enormous invisible disk stretching between galaxies. Shape matters because gravity follows the distribution of mass. A sphere tugs evenly from every direction and creates a balanced pull. A flattened sheet pulls more strongly along its plane. That difference explains why Andromeda doesn't just drift randomly, it slides along a gravitational track. But even as Andromeda approaches, the universe keeps expanding. Distant galaxies continue to rush away from us faster and faster. In fact, billions of years from now, our ancestors staring at the merged Milky Galaxy might not see any other galaxies at all. Expansion will push them so far away that their light won't reach us. But here's a twist. The same invisible dark matter sheet pulling Andromeda toward us also keeps our galaxy intact. The same gravity that heads us to collision also built a structure that lets stars form, planets grow, and life emerge. Our home Milky Way galaxy is likely much more dangerous and ravenous than we used to think. Among its billions of stars, there might be the remains of a smaller galaxy the Milky Way swallowed about 10 billion years ago. But then, after gobbling up a whole galaxy, a planet would be a little more than a quick snack for it. Should we get worried here on Earth? Not really. We're already inside the Milky Way. It's our galaxy's gravity that keeps Earth, the Sun, as well as billions of other stars moving around it. But a swallowed galaxy may mean a different thing. If the Milky Way can devour smaller galaxies, it can also take their stars and planets. And maybe some of them have the right ingredients for life, Or perhaps in the future we could relocate to those captured worlds. But for now, let's get to that poor galaxy. It's called Loki, after the Norse deity of tricks. Because this ancient galaxy has been hiding from us for billions of years, and now Loki may completely change the way we understand how the Milky Way was built. Our galaxy is enormous. It contains between 100 billion and 400 billion stars, and stretches across a distance that's hard to imagine. But the Milky Way wasn't born this big. It grew slowly, over billions of years, by pulling in smaller galaxies. That's like a snowball rolling downhill. Every time it picks up more snow, it gets bigger. The Milky Way did something similar. It collected smaller dwarf galaxies and added their stars to itself. Such galaxies don't leave behind obvious signs because they get literally ripped apart. But their stars can still tell us their story. Now, let's become space detectives for a moment. You find a strange group of stars close to the Milky Way's main disk. That's the giant, spinning, pancake-shaped area where most of our galaxy's stars live. These stars immediately catch your attention. They contain very little metal. You know for sure that in astronomy, metal doesn't just mean iron or steel. It means almost every element heavier than hydrogen and helium. But the first stars in the universe were made from only simple ingredients, mostly hydrogen and helium. Only later generations of stars started creating heavier elements inside their cores. When they eventually exploded, they spread those elements through space. So, the stars you found with very little metal are what? Yes, they're very, very old, like ancient fossils. They're leftovers from the early universe, before space was filled with that mix of elements we see today. An even cooler fact for our space investigation is that such old metal-poor stars are often found in dwarf galaxies. Those are small galaxies that the Milky Way probably gobbled down over time. And Loki might actually be one of those forgotten meals. Finding such ancient metal-poor stars in the Milky Way is kinda like searching for something small in a giant storage room. Because there's billions of stars out there. And still, scientists need to study these stars because their chemistry and movement can reveal what was happening billions of years ago. If you had started to look for those stars many years ago, you would have searched for them in the Milky Way's halo, because that's what scientists did for a very long time. The halo is a huge round cloud of stars that wraps around the main part of our galaxy, kind of like a giant bubble around a pancake. That seemed to make sense because the halo is full of old stars. But why didn't we check closer to the center, inside the Milky Way's main disk? Even bigger discoveries could be hiding there. Well, if you decided to do so, you'd come across a serious problem. The thing is, the disk is super crowded. It's full of young stars, bright clouds of gas and dust. Finding a few ancient metal-poor stars would be like trying to find a few black and white photos in a room full of Andy Warhol posters. That's why a recent discovery was so interesting. Using data from the European Space Agency's Gaia telescope, astronomers found 20 metal-poor stars sitting surprisingly close to the Milky Way's disk. By the way, Gaia has been mapping the galaxy in incredible detail, tracking the positions and movements of about 2 billion stars. Anyway, after spotting these unusual stars, researchers turned to a powerful instrument on the Canada-France-Hawaii telescope in Hawaii. They wanted to use it to study the chemical makeup of those stars more closely. The results showed something unexpected. Out of the 20 stars they studied, 11 were moving in the same direction as the Milky Way's disk. The other 9 were moving the opposite way. At first, that sounds strange. Imagine a crowded highway where most cars are going east, but some cars are suddenly driving west. Something must have caused that. Plus, all those stars had very similar chemical patterns. It might mean that those stars probably didn't form separately. They likely came from the same place, possibly a small dwarf galaxy that the Milky Way swallowed long ago. Yep, Loki. We already know the Milky Way has been through one huge collision. It's called Gaia Sausage Enceladus. Yeah, I know. And it happened around 8 to 10 billion years ago. Scientists think that the event helped turn our young, chaotic galaxy into the much calmer one we live in today. But if Loki really existed, it may have been another massive collision, almost as important as that one. Plus, it could mean that the Milky Way is still hiding more ancient meals inside it. And the next giant collision may already be set in motion. The thing is, our galaxy is part of a giant neighborhood called the Local Group. It contains dozens of galaxies, but 3 of them are the real giants: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. And one day 2 of these giants are going to collide, all because of gravity. The Milky Way and Andromeda are pulling on each other across space. Right now, they're separated by about 2.5 billion years, but they're moving closer every second. In about 4 billion years, the 2 galaxies are likely to meet. But don't imagine stars smashing into each other like cars in a traffic accident. A galaxy is mostly empty space. Even though the Milky Way and Andromeda each contain hundreds of billions of stars, the distance between stars is so huge that direct collisions are extremely unlikely. Instead, the 2 galaxies will pass through each other, and their shapes will be completely changed. Then, over the next couple of billion years, the 2 galaxies will slowly combine into one single, giant elliptical galaxy. The Triangulum Galaxy will continue orbiting the new galaxy for a while, although some simulations suggest it could eventually join the collision too. At the same time, the Milky Way and Andromeda might not collide after all. The reason is that galaxies don't move through space alone. The Local Group contains many small galaxies, and they can affect the future. Think of it like a group of people pushing and pulling on a heavy object. Even if 2 people are the strongest, one person pushing from the side can still change where the object goes. The Triangulum Galaxy could actually make a Milky Way-Andromeda collision more likely by changing their paths. But the Large Magellanic Cloud, the Milky Way's satellite galaxy, pulls in the opposite direction. Its movement is different from the Milky Way-Andromeda path, and that could make the collision less likely. Scientists added these galaxies to their models and found something no one expected. There's almost a 50% chance that the Milky Way and Andromeda will not merge during the next 10 billion years. The biggest problem is that we still don't know every detail about these galaxies. Their exact speeds, masses, and movements are difficult to measure, but even tiny differences can completely change what happens billions of years from now.
A vast galactic mystery has recently baffled astronomers. They've noticed that all but one of Andromeda's 37 satellite galaxies point toward the Milky Way. It's so extraordinary that it challenges current cosmology and might provide the answer to the dark matter question. So it happened like this. One day, scientists looked at those other satellite galaxies that go around Andromeda and spotted a really weird alignment. Now, we should keep in mind that Andromeda is kind of like our Milky Way's neighbor. It's huge, about twice as wide as the Milky Way, stretching 200,000 light-years across. It also has way more stars, around 1 trillion, compared to our galaxy's mere 250 to 400 billion. Just like our galaxy, it has a bunch of tiny galaxies called dwarf galaxies spinning around it. There are 37 of them. The strange thing is, almost all of those little galaxies are on the same side of Andromeda. And it's getting even creepier, because it's the side that faces the Milky Way. Only one galaxy is hanging out on the other side. Imagine tossing a bunch of marbles around a tree with nearly every single marble landing on just one side. That's weird, isn't it? Scientists say that this discovery doesn't match what they expected at all. Their usual space models show that stuff like this should be spread out more evenly. But this isn't even close to even. It's so lopsided that they can't really explain it yet. Those models follow the main space theory we use today, called the lambda cold dark matter model. According to this theory, the little galaxies should be spread around Andromeda pretty evenly, maybe just a bit lopsided. But in real life, their distribution is way more uneven than the model said it should be. The scientists have run tons of simulations, and only about 0.03% of them ended up close to what we actually see. And still, none of them matched the real thing exactly. So, does it show the Lambda CDM model has flaws? That would be a big deal, because we normally use this model to explain how the universe works. If the real sky doesn't match what our model says, especially in a place as close and well known as Andromeda, it might mean that we're missing something big. Another strange thing, many of Andromeda's satellites seem to lie in a flat plane instead of being randomly distributed in all directions. This kind of flattened structure has been seen in other big galaxies too, including our own, but it's still not well understood. Maybe the satellite disk is connected to the weird cosmic asymmetry, but no one really knows how. In any case, the fact that all the tiny galaxies on Andromeda's side line up almost perfectly in the direction of the Milky Way is super weird. It makes you wonder, could our galaxy be pulling or affecting them? But the catch is that nothing like this is happening to the Milky Way's own satellites. Plus, the gravity between our two galaxies doesn't seem strong enough to do that kind of pulling. The answer might lie in one of the most mysterious things the universe has to offer: dark matter. Let's start from the very beginning. We'll go all the way back to the early universe, just after the Big Bang. Now, back then, I wasn't around then, but I'll tell you anyways. Matter in the universe was spread out pretty evenly, but not perfectly even. In a few spots, there were just slightly higher amounts of matter than in others, tiny clumps. Those little differences were important, because gravity could latch onto them. Over time, those denser regions started pulling in more material, slowly growing into the first structures in the universe. Astronomers believe that dwarf galaxies were the earliest and smallest building blocks of galaxy formation. Think of them like Lego bricks, tiny pieces that were later pulled together by gravity to build larger galaxies over billions of years. Now, when we talk about matter, we mean two different things: normal matter, the kind we can see and touch, including atoms, gas, stars, planets, and everything around us, and dark matter, the invisible kind. It doesn't give off any light, doesn't absorb it, and doesn't interact with normal matter in the usual ways. The only reason we know it exists is because of its gravitational pull. There's also a lot more of it than normal matter. Scientists think that roughly 85% of all matter in the universe is dark matter. At the same time, we've never directly detected a dark matter particle. But we know dark matter is there because it bends light, it holds galaxies together, they spin too fast to stay intact otherwise, and it shapes the structure of the universe, allowing us to map its influence on larger scales. While normal matter can clump together, crash, heat up, cool down, and eventually form stars and galaxies, dark matter can't do any of that. It doesn't bump into itself or radiate heat, but it can still form big, invisible clumps, which we call dark matter halos. In the early stages of the universe, the halos acted like gravity wells. They pulled in normal matter, which sank into the centers of those halos and formed the first galaxies. So, galaxies like the Milky Way or Andromeda might be sitting inside enormous blobs of dark matter that we just can't see. So, cosmic asymmetry explained? Not yet. Scientists are sure that dwarf galaxies are some of the most dark matter-dominated objects in the universe. In many cases, over 99% of their mass is likely to be dark matter. That means they give us a unique chance to study dark matter without all the messy gas and stars that exist in larger galaxies. Researchers use dwarf galaxies to figure out how dark matter clumps together, or whether there are alternative theories of dark matter, like warm or self-interacting dark matter. At the moment, the main theory is that dark matter behaves like a cold, clumpy, and slow-moving fluid. At the same time, it might not be totally cold. Maybe it has other properties. Maybe it interacts with itself or with normal matter in subtle ways we haven't discovered yet. If that's true, it could help explain why satellite galaxies form in strange patterns, like the ones around Andromeda. In other words, the Lambda CDM model might indeed have flaws. According to it, thousands of dwarf galaxies should be orbiting around larger galaxies like the Milky Way and Andromeda. But we only see a few dozen. This is known as the missing satellites problem. There are other puzzles too. For example, Lambda CDM predicts that dark matter halos should be the densest at the center, but many dwarf galaxies seem to have cores of their own. Plus, dwarf satellites around galaxies like Andromeda and the Milky Way seem to lie in thin, co-rotating planes, and it's something extremely rare in Lambda CDM simulations. And finally, some simulated dark matter halos are so massive that they should form bright dwarf galaxies, but we don't see them. No wonder astronomers are so interested in dwarf galaxies and the explanation of cosmic asymmetry. For that, we need more precise measurements of their motions and structures and simulations that add more realistic physics, like stellar feedback, turbulence, and so on. Plus, we gotta search for new dwarf galaxies in the local group and beyond, using better telescopes and deeper surveys. Now, getting back to Andromeda's weirdly positioned satellites, if the dark matter theory doesn't work out, there's another possibility that involves large-scale interactions between galaxies. It could be an old collision or a near miss that shaped the current distribution of satellites. For example, some scientists think a smaller galaxy, Messier 32, might have collided with Andromeda long ago, stirring things up. Scientists have seen some lopsided shapes in other galaxies before, but none as weird as what's going on around Andromeda. Usually, the little galaxies around big ones spread out pretty evenly or are just a bit off. That makes scientists think Andromeda might be a super special case. They say we need to keep looking, using better telescopes, to crack the Andromeda Galaxy mystery. And perhaps, after figuring out the truth, we'll also come closer to solving the dark matter problem. A recent shocking discovery, shocking I tell you, shows that one galaxy can devour another smaller one, leaving behind just faint remains. Can anything like this happen to our home Milky Way galaxy? And if it does, what will happen to the inhabitants of the planet Earth? You know, us. Well, let's figure it out. This whole discovery is actually a curious story. Even before the Rubin Observatory, an astronomical observatory in Chile, even started its full science work, it accidentally helped astronomers spot something totally unexpected. In June, the team released its very first test images, and one of them showed a deep look at the Virgo cluster. That's a huge group of nearby galaxies scientists have been studying for years. But in the bottom right corner of that image, there was something thin and strange, and it wasn't me. It was a tiny razor-sharp streak of stars stretching away from a well-known galaxy called M61. No one had ever seen it before. Now, M61 looks a lot like our own Milky Way galaxy. It's a barred spiral galaxy with long, sweeping arms. But despite the similar shape, the center of M61 is far more dramatic. While Milky Way's supermassive black hole sits quietly, almost as if it's asleep, M61's black hole is wide awake and hungry. It feeds on surrounding matter and blasts out powerful flows of energy, which creates a kind of galactic storm that spreads through the galaxy. M61 has been studied for decades, but Rubin's camera is built to pick up things that are extremely faint. That's why this new star system suddenly appeared. It was as if someone turned on a flashlight in a dark room. Now, the stream is enormous. It's about 50 kiloparsecs long, which is roughly 163,000 light-years. That's more than the size of the entire Milky Way. Most stellar streams around our own galaxy are only a few tens of thousands of light-years long, so this one is huge by comparison. Scientists think that the long trail is made of a dwarf galaxy that got too close to M61. Once it crossed into the larger galaxy's territory, the dwarf galaxy became trapped in its gravitational grip. Little by little, powerful tidal forces began pulling it apart, stretching it into a long, faint trail of stars. Eventually, it was completely ripped apart by M61's gravity. When that happened, the larger galaxy seemed to have responded with a burst of new star-making about 10 million years ago. It almost felt like the collision kicked it awake. This process, large galaxies tearing smaller ones apart, is thought to be one of the main ways galaxies, like the Milky Way and M61, grow over billions of years. Each smaller galaxy that falls in becomes fuel for the larger one, adding stars and gas, and sometimes this process can even stir up activity around the central black hole. Will our Milky Way become that smaller galaxy one day? Well, we do have a much bigger neighbor, the Andromeda Galaxy. But at the moment, we can't predict whether it'll get hungry enough to attack the Milky Way. Whew, what a relief. Anyway, it might seem weird that the M61 stream had gone unnoticed for so long. It wasn't exactly faint or subtle, glowing with the light of about 100 million suns. Hard to miss. But it managed this trick by staying hidden behind a nearby galaxy. This makes it really difficult to detect even bright stellar streams. To find them, we need extremely sensitive instruments and careful techniques. At least now we know that giant galaxies may grow by eating smaller ones, leaving long trails of stars behind as evidence. The researchers admit that it's surprising that such a huge structure stayed hidden around a famous galaxy for so long. And it seems that the discovery of the M61 stream is just the beginning. The night sky might start filling with new, uncovered structures, ghostly trails, forgotten galaxies, and the remains of ancient cosmic encounters. The Rubin Observatory is a brand new astronomy center built on a mountain in Chile. Its full name is the Vera C. Rubin Observatory. It was named after the astronomer who first found strong evidence that dark matter is real. Now, what makes Rubin special is that it's the first telescope of its kind. Its giant mirrors, super-sensitive camera, fast movement, and powerful computers all use cutting-edge technology. The main telescope, called the Simony Survey Telescope, has a 27-foot mirror, and it uses the LSST camera, which is the biggest digital camera ever made. But we'll talk about it a bit later. For 10 years, this telescope will take extremely detailed pictures of the southern sky. It will scan the entire sky every few nights, creating a huge, high-quality time-lapse video, the largest movie of the universe ever recorded. This movie will help scientists spot things that change over time, like asteroids, comets, stars that get brighter or dimmer, and exploding stars called supernovae. To create this giant time-lapse, the Rubin Observatory will have to use a lot of new technology. Some of its parts were invented from scratch, and others were improved versions of older designs. It'll help scientists discover all kinds of things, many we already expect, and many we can't even imagine yet. Even so, Rubin Observatory was built with 4 main science goals in mind: learning more about dark matter and dark energy, creating a complete list of objects in our solar system, mapping the structure of the Milky Way, and studying objects that move or change brightness over time. Everything about the telescope, its huge size, fast scanning speed, and ultra-sensitive camera, was designed to make discoveries in these 4 areas as complete as possible. Rubin's telescope isn't the first telescope with a mirror about 27 feet wide, but it is the first to combine its primary mirror and tertiary mirror into one single surface. Putting both mirrors together is a special innovation that makes the entire telescope more compact. Because of this, it can move faster and get ready for its next observation much more quickly. The telescope's LSST camera is the biggest digital camera ever created. It's about the size of an SUV and weighs around 6,000 pounds. It holds a giant 3,200 megapixel CCD array. Just one single picture from Rubin is so large that you'd need about 400 Ultra HD TV screens to display it. It's also the fastest-moving large telescope on Earth. Rubin's telescope can swing into a new position in only 5 seconds and immediately start taking its next image. This speed comes from the telescope's compact design, thanks to its 2-in-1 mirror and its powerful drive motors. They can quickly move and stop the 220-ton telescope mount without shaking it. Even small vibrations can ruin an image, so this stability is a huge achievement. By the way, if the telescope were spinning at full speed, you wouldn't be able to outrun it. Also, Rubin Observatory has a rare combination. It can collect a lot of light and capture a very large area of the sky in a single picture. This means it can spot faint objects spread out over a wide region without needing many separate images. When you add the telescope's incredible speed, you get the perfect setup for creating Rubin's ultra-high-definition 10-year time-lapse of the universe. A fun fact, each Rubin image covers about 10 square degrees of sky. That's the same area as 45 full moons, or about the size of a golf ball held at arm's length. Another cool thing is that Rubin data will be immediately available to scientists in the US and Chile, and to members of Rubin's International In-Kind program. They'll be able to access everything through an online portal, which means that no giant downloads are needed. After 2 years, the entire world will be able to view Rubin data. Rubin will also process new images every night in near real time. If something in the sky moves or changes, the system will send out a public alert within 60 seconds. This will allow scientists to respond quickly and point their telescopes at the event. Each night, Rubin Observatory will create 20 terabytes of data and send out up to 10 million alerts about changes in the sky. By the end of the 10-year survey, Rubin will have produced a whopping 60 petabytes of raw images. It'll be the first time so much astronomical information is shared with so many people.
Is there a giant mega-sun in the center of our Milky Way? Scientists actually thought so for a while because it's the brightest place in the galaxy. It has millions of stars packed into a small area. This area is called the Gigantic Bulge. The Gigantic Bulge has millions more stars per light year than any other part of the galaxy. It can be 10 million times denser than our part of the neighborhood. In some cases, stars in this region are only 5 light days apart. That's like if there was another star in our solar system a bit further away than Pluto on a space scale. But why is this place so dense? When galaxies form, a lot of gas and dust come together under the force of gravity. This material gathers up and eventually forms stars. Gravity and angular momentum balance out, and it starts looking like a flat disk with a pretty bright, bulging, dense core. The stars live their comfy lives, and once they get to the finishing line, they collapse under their own huge weight. Then, the black hole forms. Black holes love to eat everything around them, and the more they eat, the bigger they get. And what place is more perfect for a fine dinner than the galaxy center, where all the space stuff is packed together? So it starts eating surrounding gas and dust, forming an accretion disk. As this material spirals into the black hole, it heats up and emits a lot of energy, which makes the center of the galaxy even brighter. That's why you can find both supermassive black holes and galactic bulges in the centers of all galaxies. The galactic bulge at the center of the Milky Way looks a bit like an ellipse. That's a classical bulge. Stars aren't like our sun. They move randomly in all possible directions and planes. Plus, they all move at different speeds. So gravity is going crazy there, and this makes the bulge look more like a sphere, or an ellipse. Since they were the first ones to form, they have some of the most ancient stars in our galaxy. But there are also some places of star formations and lots of younger, massive stars that are less than 100 million years old. As we move farther away from the center, things get a bit calmer. Stars start rotating uniformly and become stable. Right now, Earth is in one of the Milky Way's spiral arms called the Orion Arm, pretty far away from the galactic bulge. In our part of the neighborhood, stars are usually about 4 or 5 light years apart. This means that most of a galaxy is actually just black, empty space. Our black hole is called Sagittarius A star. It's a monster about 4 million times the mass of our Sun. It's also about 32 million miles in size, almost like the distance between Mercury and the Sun. But don't worry, it's not attracting the Milky Way inside it, and it's not going to eat us. These black holes are actually super small compared to the entire galaxy, so they can only eat whatever's around. Right now, many stars orbit Sagittarius A star, and even though it emits a huge amount of energy, we can't see its light from Earth without a lot of scientific effort. But why don't we see the center itself? The galactic bulge is so bright that even though it's 26,000 light-years away, we should see it shining brightly in our sky. Yet we don't. Turns out it's all because of space dust. There's a lot of dust between us and the core, and it absorbs most of the visible light. We can only look at the galactic core using other types of light, like near-infrared, gamma ray, and so on. NASA has images of the core in different types of light, and it shows how scarily bright the center is without the dust blocking our view. But not all bright regions are blocked by gas and dust. For example, when we look at dense clusters like the Messier 13, The stars are so close together that they look just like a white spot. Most of our telescopes can't separate them from each other. The satellite galaxy M32, our neighbor near the Andromeda Galaxy, has about 84 stars per light-year. It's so dense that stars can't be resolved even by the Hubble Space Telescope. To get the idea, our solar system is 2 light-years long. We'd see about 168 stars outside our window if we were there. Our closest star is Alpha Centauri. It's about 4 light-years away from the Sun. If it was just a couple of light days away, it would shine much brighter than the full moon. So if we somehow managed to survive in crazily dense star regions, the sky would be white all day long. But it's unlikely that we'd make it. As we get closer to the center of the Milky Way, the chances of finding life get super slim. The gravity of stars is going wild with chaotic movements, so there are barely any planets around. On those miracle planets, the radiation from cosmic rays is skyrocketing. Supernova blasts and star collisions nearby become an everyday occasion, and all the gas around makes it basically impossible to breathe or even see properly. At the same time, as we move further away, there are fewer stars around. Elements that are super useful for life, like carbon, oxygen, and iron, are produced by stars, so they also drop. Too much radiation is awful, but too low radiation means that there's not enough energy to support chemical reactions, like photosynthesis. Which is why, if there is extraterrestrial life, it would most likely be somewhere in the middle of different galaxies. But some galaxies get their brightness from a so-called active galactic nucleus. These are extremely energetic regions at the center of some galaxies. They shine much brighter than any stars imaginable, although it mostly shines only in certain parts of the electromagnetic spectrum. The brightness comes not from the stars, but from the accretion disk around their supermassive black holes. As the material slowly falls into a black hole, it gathers around it and creates this flat, spinning disk of gas, dust, and other stuff. Since the gravity and friction there are insane, this disk heats up and starts emitting enormous amounts of energy. Also, this disk spins incredibly fast, almost at the speed of light. Because of that, collisions there happen all the time, and they're unimaginably powerful. They release even bigger amounts of energy. Most galaxies don't have an AGN. Those that do, like the galaxy M87 in the Virgo constellation, are called active galaxies. There are also different types of AGNs: the Seyfert galaxies, radio galaxies, and finally, the winners of our space brightness competition, quasars. Imagine things so bright that they can outshine the entire galaxy they belong to. Quasars are a specific type of active galactic nucleus, the most extreme and luminous form. They belong to the supermassive black holes, the biggest ones in our universe. Quasars are like a combination of several things. First, they're the brightest accretion disks in our world, because of their behemoth black holes eating everything around. But they have some cool features. For example, they have powerful jets of particles that shoot out from the poles of the black hole at nearly the speed of light. These jets add up to the brightness of the quasar, although they can only be seen in radio wavelengths. The energy they emit is so intense that they can be seen billions of light-years away. However, the nearest quasar to us is 600 million light-years away, so we can't see them with backyard telescopes. So, when we look at a galaxy through a telescope, we usually see only the brighter core, not the outer parts. Unfortunately, our eyes just aren't made to see things like the active galactic nucleus. So, these stars are the brightest things we can see. But what a beautiful sight it is.
This is our home planet Earth and its satellite, the Moon. Zooming out, and here's our solar system. A bit more, the Milky Way galaxy. And we're a small dot among an infinite number of stars. Now, even farther out, a cluster of galaxies. Dots and swirls in the endless space. Further, there's Laniakea supercluster. That little dot here is our galaxy. Moving on, Hydra Centaurus supercluster. Huge clusters comprising thousands of galaxies are no more than a speck from here. Next, Pavo-induced supercluster. This is an area 200 million light-years wide. We can zoom out until we see the entire observable universe. Each little dot in here actually contains thousands of galaxies and quadrillion stars. Scientists speculate that our universe may look like a bubble, and that bubble might collide with another universe. Yes, other universes could exist. Actually, even a whole infinite number of those. All of them could have appeared after the Big Bang. The collision between them isn't impossible either. At least, it might have happened before. And the proof is here, in the direction of the constellation Uranus. This place is called Uranus Supervoid. It's about 1 billion light-years wide. By comparison, the width of our entire galaxy is only about 100,000 light-years. There's absolutely nothing in this place, and it may be a trace from an old collision between our universe and another. Scientists think they were passing by each other. When the distance between them was minimal, the gravitational forces of the bubbles began to pull toward each other, just like two drops of water trying to connect when they're close. But the speed of the universes was too high for them to continue interacting. So the other universe just tore out a piece of our bubble. There might have been about 10,000 galaxies in that void, and all of them were either destroyed or taken over by the other universe. Let's travel to the edge of our universe to see how this collision might have taken place. We're 10 billion light-years away from our home. Here, in another galaxy, we see amazing nebulae of different colors and shapes. And if you look in the other direction, there's a huge wall moving at us. All these bright sparks on it are enormous galaxies about to collide with us. But in fact, it's a humongous mirror that only reflects our universe. Here, space-time is distorted and begins to be pulled into another universe at a tremendous speed. The usual law of physics may simply stop working at this point. Gravity may disappear, and with it, all the stars would explode and people on the surface of planets would hang in weightlessness. But if the universes didn't go at a tangent but crashed directly into each other, things would be much scarier. The enormous amount of collision energy would probably cause an incredible explosion. Its force would simply destroy everything in our bubbles. Still, the two bubbles might begin to merge too. At first, all galaxies at the edge of the universes would be torn apart. But then, the merger would begin. The galaxies would start moving chaotically. They would fly past each other, break apart, collide, and explode. The collision of two galaxies is an accident of enormous proportions. And it might happen to our home quite soon, in space terms. The Andromeda Galaxy is heading our way. It's a spiral galaxy about twice the size of ours. And there are about 1 trillion stars there, which is twice more than in our Milky Way. At the very center of this bright galaxy lurks a dark beast, a black hole. Its weight is 2 8/8 of the Sun's mass. Red giants hundreds of times larger than our Sun. Pulsars emitting enormous amount of energy like spotlights. Rogue stars, and many large and small black holes. This soup of dangerous objects is moving toward us at 68 miles per second. A trip to New York to Los Angeles at that speed would only take half a minute. The disk of Andromeda can already be seen with the unaided eye on moonless nights. As time goes on, it'll get even bigger. As Andromeda gets closer to us, its gravitational force will begin to stretch the arms of our spiral galaxy. It'll begin to unwind. The stars and planets will lose their orbits. One possible scenario is that an unknown asteroid, or even a dwarf planet from the Andromeda Galaxy, will crash into the Earth at an incredible speed. Our planet will explode just like a balloon from this impact. Oh, goody. Another option involves stellar collisions. Our Sun would face another star. The bigger star will slowly begin to consume the smaller one. First, it will steal the light upper layers from it, and then it will eat it just like spaghetti. Or even like rigatoni. When a large star reaches its critical weight, it will burst. This explosion will destroy everything around it, including our solar system. Perhaps the shockwave will even reach other neighboring stars. Yet another scenario is that our solar system will be thrown into dark space. Imagine a tennis ball tied to a rope. You take the rope and spin the ball over your head like a sling. Then you let go of the rope and send the ball flying. This is what will happen to the Sun and all the planets around it. We'll find ourselves in dark and cold space. But life on Earth will not be affected. We'll still have our bright star to keep us warm. The only disadvantage is that all the stars in our night sky will disappear. And the most likely possibility is that the merger of two giant galaxies will have no effect on us at all. The thing is, the distance between stars and planets in space is enormous, so they can all just mix together and form one giant cloud. It would be like shoveling fine sand through a big sieve. The objects won't interact with each other. But the most interesting thing will happen to the black holes in the centers of our galaxies. Right now, there's a dense cluster of stardust and stars around them. As Andromeda and the Milky Way come closer together, they will begin to dance with each other. Gee, will it be the twist or the foxtrot? And when the black holes get close together, they'll begin to swallow all matter around one another. Billions of tons of colored stardust, asteroids, and star particles will fly toward the very center of either black hole. It might seem like this process happens very slowly, but it's an illusion. Super heavy objects like black holes warp the space-time grid, so time is much slower near black holes. And all objects that seemingly stay on the event horizon for weeks or even months are actually long gone. When the black holes finally come together, they merge into one supergiant black hole, but its mass is slightly less than the combined mass of the two dark monsters. Some of their weight is transformed into collision energy. This energy is released so strongly that its waves can be felt in other galaxies. Now, a huge black hole gathers all this dense and hot core of the two galaxies around itself. At some point, the black hole feels full and throws out powerful jets of energy into space. This is called an active galactic nucleus. It's one of the brightest phenomena in the universe and the most powerful source of electromagnetic radiation ever known. These jets may be more than 5,000 light-years long. By comparison, the distance from Earth to the nearest star, Proxima Centauri, is only 4.2 light-years. And the explosion that accompanies the jets has the power of 100 supernova explosions. Wow, blows my mind. The blast wave from this event could even reach the edges of a new galaxy, and this outburst would be visible from millions of light-years away. Now, there are dense clouds of multicolored dust at the center of merged galaxies. The weight of these clouds is so great that they begin to shrink and take on a round shape. Gradually, they become so heavy that they compress the core and nuclear reactions start inside them. The temperature begins to rise and soon, boom, there's a supernova. It's a veritable fireworks show at the center of the galaxies. Stars erupt from the fog and form new hot worlds. At this point, the arms of the two galaxies that were previously pulled out slowly return to their former shape. The super-heavy center of our galaxy has such a gravitational force that it affects stars and nebula hundreds of thousands of light-years away. The galaxy's arms twist again, and we see the new and finished galaxy, the Milkomeda, or Milkdromeda. Hey, how about the Milky Way? Blah blah blah. Well, that's hard to say.